So hello everyone. It's my pleasure to welcome you to the last talk session of today, the book-based cryptography session. To start, will be made by Massimo Ma, who is soil arrangement equally related to developing OHCP to incorporate.
Hello everyone, and it's the Andre for the introduction. Yes, this is the joint work with Canon Love and Others. All right, so the topic of this talk is about foundations of the base cryptography, and more precisely the hardness digital version of the decoding. And this is what I call the randomness in. But more than the results, we are actually interested in the techniques because it's known for a while that the problem is hard, but it's the techniques that we have have some inherent limitations, and by changing the techniques, finding new methods, we hope to improve. And indeed, there's been a very recent trend in the cryptography to try and adapt techniques from repeated lattices, which are far beyond code, at least in terms of foundation. And in particular, the OHCP technique, for Oracle, we see that's a problem, which has been introduced by Begev and Stephen David Stock in 2017, is now the modern way of dealing with reductions in lattices, and especially for structural values. And in this paper, we adapt the OHCP technique to the Hamming metric, which was an open problem, or it was thought to be really inherent to lattices. And as byproduct, we get a worst case advantage reduction for the decisional version of the decoding problem for some non-trivial set of parameters. And we hope that it paves the way to get reductions for structure. All right, so this is a session in code-based cryptography. So, most of you, if not everybody, is already familiar with the decoding problem, but let's recall it again. We are given a linear code, which is specified, let's say, by a general matrix G, and a noisy code word, where the error vector has some sparse distribution. And the goal is to recover the secret. First, it's a very old problem, and for cryptographic interest in the set of parameters, it's the best version are exponential errors, it's at a high level. So it's a problem, and this version is an average case situation where you give distribution on your inputs. You take the general matrix at random, and you take your noisy code word also random. And the question is, there are many different distributions you can put on T. Let's say sparse. For instance, T can be uniform over a set of given Hamming weight, or it can be formed by multiple independent undivided. And in this situation, this problem is also known as non-type, which recalls it's a problem with Oracle, which has a secret S and some media, which gives the noise parameter. And the Oracle will output a pair of elements, first a uniformly rounded vector and the inner product between this uniformly rounded vector with secret and some additional value. Says you can see that if you gather n samples from this oracle, then to matrix, you just get an average case version of the decoding problem for codes of low grade, which depends on the number of samples. All right, and this problem has been introduced also for a while, but it's only recently that we got the worst case reduction for this problem. It was introduced by Rakowski, Wachowski, by Internatan and Dish at Asiacrypt 2019, and later revisited by Yu and Zhang at 2020. But as I said, we are interested in pseudo-randomness. So we are interested in decisional version, where instead of decoding, we really want to distinguish between two situations. First, we want to distinguish between the word of uniform here and the noisy code. D has also from this party solution. Fortunately, we know that this problem is actually equivalent to the third version. It's a decision reduction, for instance, one is Fisher and Stern in Asiacrypt 96. But this reduction is fundamentally average space to average. So on the one hand, it's very good for crypto and it's very tight. It's tight can be. On the other hand, it cannot apply to more involved structure on the matrix. It really needs the G to be taken uniformly at random, the set of all matrices. And well, for this to be practical for cryptographic applications, actually we need to consider structural lines. And by structural, I mean, for instance, G can be chosen that formed by multiple blocks, for instance, circulant matrices here. This is known as quasi-cyclic code. And it is very interesting because it allows to compress your matrices. Any certain matrix here can be represented by a polynomial of degree at most the group size. Such that the matrix vector product is nothing else than a product of polynomial in cyclic polynomial algebra. And now you can rewrite noisy code word as just a bunch of noisy polynomials. Here I just consider the example. An example is just one row and two blocks. You can consider multiple rows with block. Just change a little bit this, but it's not difficult. So this yields to you can translate the decoding problem into this setting. You consider your ring R, for instance, your cyclic algebra, and you can translate the search problem and the decision problem. It's just a mere translation of what we had before. And there are actually those problems are really interesting for crypto because they are the core of two of the three remaining candidates for the list competition, like in HPC. And they are also found their way into secure multi-party computation in the past few years. But the problem is, okay, the third version is still very clear. We don't know much on the generic decoder, can improve, but still a hard problem. And the decisional version is widely believed to be hard, but on the theoretical side, we lack foundations. It's pretty mentioned, the knowns of such a decision reduction, they do not apply on the same. And we only have very specific parameters where we can actually give reduction, and it's just very basic. On the other hand, when we look at the world of Euclidean lattices, then the world is bad. There are a lot of reductions for many flavors of degree and many set of parameters, which I put some of them on this time axis just to see where we are. Sorry, it's not exhaustive at all, and structural lattices were used before this origin, which I put at the introduction of ring algebra. But still, I remember this because it's the paper that gives a reduction, a substitution reduction for ring algebra. And then for the next years, some constraints that were introduced that were needed for the reduction to work, they were somehow mitigated up until 2017, where we have just changed the introduction by Packard again and 7 Davidovich of this OHT technique, where now basically all the previous restriction were removed. And this technique has been used many times later. Now we are really for the case of codes, basically we are still in the part. We are really at the limit here. We know basically everything at this point. And so the next question is, can we go beyond this barrier and go into this is the topic of this. Basically, what we get, so we adapt, we could answer it yes, we can adapt the technique for the problem, and we get a search decision reduction to the worst case decoding problem for some not trivial set of parameters, not that great. They're actually the same as previous reduction. And for the reason for that is because the main limitation is the first step, which is common between our technique and however, I believe it's still interesting because this method completely bypasses earlier reductions, and in the sense that we could actually use this vertical reduction because it's very tight and it can be composed with this. But there is this limitation for code, and with this new back, we completely ignore previous limitations, and we hope that it can be used for social cause because, in fact, everything works really well for social cause up until like very end, and I believe it's just a technical detail which didn't really become part of this paper, but I believe it can be done in the near future. So there is hope. All right. So let's dig into a little bit into the reduction. So, as I said, the starting point is actually the same as from like I said, Al and Jean. And it starts from a very simple operation, which was before, but we used in this paper. Is that so? You start from a noisy cover, as university, which is fixed because we really want the work case enough. It's fixed entirely. It's one and for all, and you want to build an NLP environment for every protocol. You need many samples. You need to be able to give fresh samples every time, and the idea to do that is to sample some random vector from some distribution, which here, which I wouldn't specify here for now, and you just take the inner product between the noisy covered and this random sample. Now, if you know what it means, it's nothing else than now an example where I call A this function R, and the noise is T times. Seems very good, but there is actually two caveats. The first one is for to have an example, we need R to be uniform, and so that's one thing. And the other thing is that now the noise TR is actually correlated with A. It's not good for one example, so we need to take care of that, but it can be done, and results some work using the notion of specific distribution. When you choose carefully your distribution R, you can prove that this construction gives an oracle as close as it can be from different smoothing distributions and parameters. I'm not going into details there, but it has attracted a lot of work in there. All right. Here in this work, in particular, we really consider the situation of smoothing by Bernoulli noise. So you want to sample more from a Bernoulli, and this for one reason which will be clear in the next slides. But first, I want to stop a moment here because I use another notation for my Bernoulli. My parameter omega is not usual success probability, but we will consider instead the logarithm of the byte, just to change the variable. Here. But the advantage is that now this is just a binding of lemma. If you sum two Bernoulli on the variable, independent Bernoulli on the variable with parameter omega 1 and omega 2, it just sums the variable. So it's clever, but it allows to simplify a lot of the formulas and it's easier to understand. And indeed, when R is equal from a Bernoulli, if you take the linear product between T and R, this is nothing else than a linear combination of T Bernoulli. So given this simple observation, and with my notation, it's just a Bernoulli of parameter omega times the weight of T. using this value noise. We want this to get as close as possible from any samples, so we really need to use missing bounds for the value distribution, and we actually need more involved one from this paper by the Salazar. So, okay, so if you have this, which is statistically close to an example, if you have an LTN solver, you just run your solver, recover S, and you're done. This is at a high level, at least, to reduce worst case. But here, we don't have an LTN solver, we just have a distinguisher. We need to do a little bit more work. I call my distinguisher, I call it A. Basically, A can distinguish between two LTN distribution or some parameter between 0, and LTN infinity is nothing but just the uniform distribution. So it's really my distinguisher between LTN and uniform. But the very simple observation is A can actually be given anything that is well typed. You give a different LTN oracle, you can run your comparison in this oracle, you get this number of queries, and it will accept or reject your samples with some probability which will depend on the parameter. And what you know is that since A has advantages n, by definition, it will accept the LTN record for parameter omega 0 with probability 1/2 plus epsilon. This is the definition of advantage. And on the other hand, it will reject this LTN infinity with probability 1/2 epsilon. So it will accept the probability 1/2 minus epsilon. So we know the extreme order of this but P is completely unknown in between. Nevertheless, it can still be estimated. We can run many times, and it's not hard to approximate this function. And what we know is basically that if we draw this probability, so we know the behavior of for example, here, we know here, we don't know anything else here, but we know that on overall it should decrease because P is nice enough. And so the hope is that using this change of behavior here, we should be able to get some information. So we start again from first, and the reason is that we want to recover the secret S. It's equivalent to recover the error T, and it's actually enough to recover the support cost. So the idea is to run through all integers 1 to n, and to ask the question: is I in support? Is Ti 0 or is Ti not 0? To do that, we can actually consider another vector V, which is direct, which has a non-zero element I and 0 everywhere. And now if you sum V to your noisy codeword, and what you get is the noisy codeword of weight T plus 1 if I was not in the support, or of weight T or T minus 1 if it was. You might have some constellation. And if you do exactly the same, basically what you get is those two situations. The hope is to be able to distinguish between. Actually, it's not clear how to do that because we might be anywhere in the curve, and the behavior of the function is not known exactly. So it can be really messy here, but the clever observation by Dubitz, their paper for lattices, is that you can actually distinguish between you can compare two oracles. Like that, so we have one oracle that we did by adding on vector, and we can also consider the same oracle where we don't have the and these are actually connected because the algorithm will accept the new oracle with probability, which is just a shift from the acceptance probability of the original. And actually, this shift will be strictly greater than 0, and we can cover this if I is not support and So what that means is that the curves are just the curve for this new variable will be slightly left or right of the original curve, and the technical observation like I said a bit is that when d is nice enough, then we can actually detect this shift in polynomial time, and this is actually true for a problem, and those constraints are measured by sensitivity among the systems. So graphically, we just have a sheet of curves, and we can really detect this. We can decide whether I is support or not. But yeah, so it's good. So you run for every integer one n, and you recover the support of t, so you recover you decode it. Okay, so far so good. The question is, can we do that for structure code? Because it was the main motivation. Actually, yes, everything works similarly. You can consider your noisy code. Just for an example, I take again the matrix. Actually, the smoothing the A times that R here can be handled. It's not, I mean, it's not trivial, but this is not scary. What is a little bit more difficult is the noise. And just to give an intuition why it fails, or just consider just one C times R, and I consider the polynomial representation of this. This is the structure version. So when you write the thing, it's really easy to see when it's just somehow a convolution product here. So what you get is that it's a polynomial whose coefficients are Bernoulli variables of good parameter. Everything seems to work perfectly. We can do the same analysis. Well, not so far. Actually, they are not independent. So that's this noise distribution is actually trickier to understand. And if you average on T, then it behaves really nicely. It's really what you expect. But it's not simply not good enough for reduction. So it's the technical reason why it fails here. And I hope that I mean if you know how to handle this distribution, I think we can leave it. Okay, so let's conclude. So yeah, the main question here is can we improve reduction to make it work for a certain situation? And yeah, another interesting question is so with this work we showed how this technique which relies on this technical lemma can be adapted to the metric, which is having metric. And the natural question is, can it be adapted to other metrics, for instance, other LP norms for maybe the rock metric? And this is still. Thank you very much for your attention.
Thank you. For questions. So you said that the parameter regime to which the reduction applies is basically the one for which the reduction is previously applied.
Yes.
Is there an initial explanation?
Yes. Actually, it's just that we are limited by this first step about smoothing techniques because I mean, if we just compose the height reduction that we have with such a version, then we just don't lose anything. So we can compose this previous trends, so we get actually these parameters. And the same thing applies here because this OS technique, we don't lose much in parameters, and the real loss is really the smoothing techniques. So if we know how to improve on smoothing bounds, then we directly improve the function. So yeah. So I mean, now it's maybe a question of philosophy because maybe you can. I mean, if you have the worst case hardness for this problem, it can mean that either it's a really easy problem, or maybe I mean, either the worst case is really easy for the parameter, which can expand, or Yeah, the question is, well, I mean, I don't know if we really want to improve on this bond, but anyway, if we could do that, then we could get better balance.
Thank you very much. Are there more questions?
Hi, thanks for that talk. My question is, I noticed that your reduction is from the code problem to lattice-based LPN problem. And as far as I'm concerned, LPN they define on the boundary field. So does it work on other field?
Yes, exactly. The reduction works perfectly for a larger field. It's really best to write the formulas because then the analysis gets messier. But the main bottleneck is the smoothing bounds and the smoothing techniques. I mean, it's those papers about the smoothing techniques are really papers. They really study the distribution for the binary field, but there is nothing inherent to binary fields just because analysis is really ugly, but it can be done. And yes, I believe the analysis can be done for a few for the smoothing. And if you have the smoothing for a few, then everything else works for it. The talk that I gave today, there is nothing which is inherent to everything works for it.
Thank you.
Is there more questions?
Who's the next speaker? Speaker. The next speaker. Yeah. Yes, yeah. We both came down.
Long wide range for you.
Everyone, will use also in this paper. In this paper, we consider fundamental cryptography using mathematics. We consider localized structure for ranker errors, decoding problem, and LRPC codes, and their applications to crypto systems. Cryptography is a branch of PQC that currently uses metric, ranker metric, and D metric, and so on. We consider ranker washing for short, rank-based cryptography. In the ranker metric, coordinates are in FQM, a field extension of FQ of degree M. For basis, any word can be expressed metric. The rank weight of X is defined as the rank of metric. The rank port. The rank support of the word is F plus S of generated by its coordinates. The rank weight is equal to the dimension of the rank support. The weight and the support definitions can also be extended to the matrix. LRPC codes is defined by the metric parity check metric of small rank weight. two classic problems find the small rank error. For standard error and standard LRPC codes heavily check the metric. Their coordinates are comes from the same support. In our case, we divide into the arrow block arrow block require them all supposed to be maturely disjoint. In this paper, we study blockwise error, the forms of support and coefficient matrix, blockwise rank decoding problem, finding errors, complexity loss, blockwise LRPC codes, decoding capacity, decoding failure probability, decoding capacity, improved accuracy ruler with smaller bandwidth than HQC like classical mechanics. This is the blockwise error. For standard error, the support metric is a metric of M by R. Coefficient metric is a metric of R by A. For errors, so more differently, since all support are maturely disjoint, coefficient metric is block diagonal forms. Two variants of decoding problem. They are find the errors. We do much work to estimate the complexity loss. As the complexity, best attacks using this reduction. So solving LRD problem defined by NK linear code is reduced to find a error code word of weight R in NK1 linear code CY. Then using equation 1 and equation 2 solve problems. There are two attack methods. Combine notarial attacks, guessing the entries of S and C, then solve a linear system. The cost depends on the guessing way. For example, in this equation, if we guess S, we will obtain a linear system in C. If we guess C, we will obtain a linear system in S. Another one, algebraic attacks. So multivariate of all linear systems in the entries of S and C by some sophisticated transformation. The cost depends on the number of entries and S and C. We adapted some typical attacks, HT and OJ, a new letter polynomial, maximum minus modeling. With two LRD problem, we obtain these complexities. This is a brief comparison. Solving RD and solving LRD. The game of most attack benefits from the blockwise structure of L. errors. OG and MM modeling, the block diagonal form of coefficient metric C allows to solve multivariate or linear system with less variables. Agility is limited because its cost depends on how to successfully get a space that contains the support of error. A new letter polynomial attack. The errors allow to divide the error ID problem into error problem with smaller parameters. We obtain the best attack is MMO modeling best attack. Finally, we obtain complexity loss of factor error in phonics. When error divided by n, error divided by r. This is simulation. This is error blockwise LRPC codes. The parity check metric be divided into errors and metrics. Each one is small weight, and all the codes are purely disjoint. This is a decoding algorithm. Decoding steps consist of computing signal S, recover support E, recover the error E. For recovering support E, we first recover E1, E2, and EL. Then we recover the whole support E. Decoding is efficient, and decoding failure probability can be any small. Decoding capacity is still achieve a single weight. This is a kind of factor error in decoding capacity compared with standard LRPC codes. This is a new observation. This code can decode the weight of close to rank GV bound. In rank setting, using ideal structure comprises size, accuracy, and word. So we must use ideal structure to ideal variant of problem and LRPC codes. On this map, vectors are equally viewed as polynomial. Px is set as a reducible polynomial for security. The ideal matrix introduced the product of polynomial can be expressed by vector and metric product. In ideal LRD and LRPC codes, we use generator metric and parity check metric consist of ideal metrics. In improved accuracy, we use two errors, three errors, and Gavin Turing codes. The security is depend on 2 RSD and 3 RSD. In improved ruler 1, km, we use two errors and RPC codes. This is ruler 2, like ruler 1. Its security depends on two ISD problem with zero syndrome and non-zero syndrome. The one of zero syndrome is derived from the indistinguishability of two RPC codes. Improve the ruler 3, km. We use two arrows and three arrows. Its security depends on two RSD and three RSD. This is the size and DFR by making trade-off between the hardness of blockwise problem and the decoding capacity of the blockwise RPC codes. We improve the accuracy and the world system. We obtain 2.5 KB bandwidth. Our accuracy has smaller sizes than HQC like classic list and oral growth. Overall, the gain of using errors and RPC codes in decoding capacity, both the complexity loss in solving blockwise RD. We need 2 points. The security strength of original ruler 1 and they do not achieve the planned security level due to structure attack. We will update their parameters and comparison at ePrint, and the potential structure attack do not influence the advantage of my function. This is the performance. We implement ruler and their original version on ZMS. Set scripts for implementation the complexity of element modeling in this website. In the future, we will do more analysis on blockwise LRD problem to obtain the gain of vector error for the combinatorial text. More analysis on indistinguishability of the blockwise RPC codes. Analyze blockwise rank support the learning problem. Decrease DFR of local and outgrowth R to standard security level. Achieve the bandwidth of about 2 KB for LEC and local. 5. Construct blockwise crypto system without ideal structure. This is new progress as last night. Combine our blockwise structure, the new improvements of RQC and rule has appeared at different. They get a slightly smaller size than the that is the best type. Achieve 1.4 KB Data is Kyber 1.5. Data is a reference. Thank you for your attention.
The elders having always the it's developed. It's like a natural translation of this regular single people. On regular the fact is those maybe translate are translating them to this rank thing and improve it.
Now there's no regular attacks.
Thanks for that, Tom. And my question is, we know in the heavy metal, LDPC code is unsafe, but each structure has many attacks on it. So, why LRPC codes are still safe now, and why do you think it is more safe than the heavy metals?
In heavy metric, we tend to use MDPC codes.
In rank metrics, we still use LRPC code, and why does the attack on heavy metrics not works on rank? And do you think rank metrics are more safe than the heavy metrics based post rifle systems?
In heavy metric, LDPC codes, each row is low heavy weight. But in rank metric need to sometimes to control.
Yes, thank you.
Talk will be given by Andre Esser, and it's on CIS Euro. Yes,
Thanks for the introduction. So this is joint work with Chris Mayans at DTU, Carlos Fox, and Eyal Olin at University. And the focus of this work is the syndrome decoding the ad signature scheme was presented in crypto last year by, I will not try to pronounce his French names, but this is currently, I think, the most competitive code-based signature scheme. So if you look at the sum of signature size and key size, this beats all the other schemes, and also in terms of signing time, it's pretty competitive. And so how does the scheme work? Back to the new slides. Built from an identification scheme. And the identification scheme is built on an MPC-that paradigm. So we have a protocol between the prover and the verifier. The prover begins with a lit case, with compute with W, lit method rather, W, sets the verifier. Protocol public coin, which means the verifier sample challenge randomly challenge space. sends this back, and then the prover answers the response, and the verifier takes the whole transcript to the public key, runs the verification routine, and outputs reject. And so, if you have seen the talk yesterday about threshold secret sharing for emptying the hat, you already know this, that emptying the hat is an approach that you can use to build post-quantum identification schemes starting from any one-way function. What you do is you essentially simulate a multi-party computation that runs or evaluates a function f on some value x, which you choose uniformly and random in the beginning, and proves that you know such an x such that the output of the function is y. So in the setting, y is your public key and x is your secret key. And this concept is actually used for at least 9 of the 40 proposals signal on randomness. Yeah. And so from the identification scheme, you go to the signatures. So let's briefly look at how this identification scheme looks. So key generation is really just sample random x. You evaluate f on this x and get y, and then you sequence x, y. In the commit phase, the prover first takes the input and secret shares. In this case, it uses an additive secret sharing. So if we're simulating n-party computation, then we sample n-1 secret shares uniformly at random. The last one we actually have to compute as a function of our original x and the sum of the others. So this actually gives a valid secret sharing. This is important to remember because these random x can actually compress. And this is for short c, then expand this. For each of them, the xn is actually large. So this one has to have the size of the secret input. And we set this on random tapes for the parties, and then we commit to each party's beginning state, which is the secret share of x, and the random tape separately. After that, we run a multi-party computation for each of these parties. And this multi-party computation actually does broadcast communication, so we can compute all the communications of the different parties. I'm cheating here a bit, but what happens is the output communications of these parties are actually such that they sum up to 0 if the secret, like the xi, are secret sharing of the range of y. Right? And then I'm outputting all the commitments and all the communications. Then the verifier samples the uniformly random challenge, and this challenge tells me it's between 1 and n, and it tells the prover which party not to. So all parties get opened except one. That's the one indicated by the challenge. And this opening then in the verification routine allows the verifier first to check if the commitments were correctly computed for these n-1 parties. If the communications are actually correct, so it just runs the multi-party computation again and sees if it obtains the same alpha I. And then it verifies that it actually also produces right? And if all this goes through, then it accepts, otherwise. So why is this whole thing secure? Honest verifies their knowledge, something we need to simulate signatures of later signature scheme. And this is something that follows from the secrecy of inputs and ethics. So even if I corrupt n-1 parties, I cannot learn anything about space. Soundness follows intuitively from this cut and choose approach. So if all parties behave correctly, then the computation is actually correct. So this means if I want to cheat, or if I don't know an X, which is actually a pre-image, then this means that I have to manipulate at least one party, and I will get caught in doing so with probability 1 minus 1 over the number of parties. Right? Because the only case where I don't get caught is if exactly the challenge indicates this one party that I manipulated and this remains. And actually, the protocol often usually a special soundness, which means that if I have two valid openings for the same commitments for different challenges, then this actually reveals all secret shares, and therefore I can actually extract this. Okay, so the idea of this Crypto22 paper was to apply this coding, and this is actually pretty nice because the coding is a linear function, and linear functions are easy to compute in MPC because you can do all the linear computations actually locally, which means you don't need any communications. At the same time, actually, if you would just run the MPC protocol as I described it, then you would prove that you know an X such that H times X is Y. This is something that's actually not hard. Right? So linear algebra, you can find such an X pretty easily. The problem only gets hard if I put a weight constraint. I ensure that X actually has at most weight omega for a reasonably small omega, then this problem becomes hard. And so I somehow have to include this picture. And this is the more or less, I think, where the novelty of this paper was. So they proposed to use some polynomial zero test. So they would actually derive from the X polynomials S, Q, P, and then in addition they have a public polynomial F. I will not explain how it works, but they are such that you compute from these polynomial T, which is the constant zero polynomial, whenever the weight of X was at most omega. Right? And now I can, of course, so I cannot hand out this polynomial. I mean, I can, of course, output the zero polynomial, this won't do anything. I cannot hand out the full computation of this. So what I do is I actually check that this gives the zero polynomial by evaluating polynomial at a bunch of points. I could simply evaluate it at the degree of the polynomial many points that I was convinced. This would be quite costly. So what I do instead is I evaluate it at random points, and as the degree D polynomial can at most have few roots. If I evaluate it in sufficiently many inputs, I actually get more and more convinced that this has to be a zero polynomial, and every time zero. Right? The problem is that this polynomial evaluation actually needs multiplication, which needs at least one round of interaction. And in addition, you need the talent points where you're evaluating this polynomial, which also means I need an interaction with this. So I end up with a 5-round protocol, which looks like this. And this is doing essentially what I said for this protocol. So at the beginning, I compute my secrets. It's a bit different here because I'm actually deriving this S from X. And so X is never secret shared, but S is secret shared together with Q and P. So it's polynomials from which I compute the T polynomial. I sample the randomness. I commit to all these shares as the state of the parties in the beginning. So go to the verifier sends the challenge. This first challenge is actually there to give me the challenge points of which I have to evaluate the polynomial. In addition, it also gives me challenges for the multiplication, but let's ignore this. Then I'm running the multi-party computation, which evaluates the polynomial on its points. I send the communications over, and then I get a second challenge, and this is actually the conventional MPC the head challenge, which tells me which party needs to open, and I send over these remaining parties. And then the verifier verifies as before that everything is with the initial right. There are two improvements that have been published before. So on the one hand, you can use a tree PLG to generate these secret shares of xi or of the polynomials, and also the Ri that moves you from opening information which is linear in the number of parties to an opening information which is logarithmic in the number of parties. You just have to give you a sibling path in the PLG tree. In addition, there was this hypercube approach, which we published at Asiacrypt this year, which says, on the one hand, you can do an n-party computation by just doing, or you can increase n at a rather low cost, and in addition, you can do kind of d times iteration of the protocol with only one auxiliary secret share, so only one of the secret shares which you cannot press. I'm not going into this because I don't have time, so if you're interested in this, take a look at the paper. These two things we actually also cover. So what we actually did was, all this was there before, we looked at the security. And in the original crypto paper, the identification scheme was proven secure, and then they gave a random oracle on proof signature scheme. But the question, of course, is this whole scheme is totally uninteresting for test adversaries, because we've got far better schemes in terms of classical security. But it gets interesting if we're considering quantum adversaries, but then you actually have to consider it in Q-ROM. And so, how to do this? Well, it's a Python protocol. There are generic results which tell you something about the security of Python via Shamir, and they are horrible. Tightness is also somewhere at I think Q to the 6 over epsilon cubed. So this is really something you don't want to apply. Or at least if you care about actual tightness, this is totally irrelevant. There is a second paper, also from Crypto 22, which actually gives you as tight as it gets result for committed open identification schemes. And we have a committed open identification scheme, so this is great. The problem is this one's only for 3 round. So our first intuition was, okay, we just start extending this result to 5 rounds. But then, actually, while working on a hypercube, I noticed that the SD in the head paper showed 2 special samples. And this is something that's a bit strange, because while we were working on the MQBSS paper a long time ago, we noticed that 5-round IDS that have 2 special samples, usually you can compress 3-round applications. At least if you have perfect 2 special samples, then this always works. You can actually just ignore the challenges you can set at the constants, and the scheme still has to be secure. That's something we showed. The problem is this is actually not really what happened here, because we don't get perfect 2 special samples, but we get some form of statistical samples, because you get the soundness error from this polynomial zero check, and therefore this proof actually doesn't apply here. But we figured out we can do something similar, so we can apply some kind of cheap Shamir transform to the first round, or to the first challenge round. And so we replace the challenge by a hash of the commitment. This is kind of standard Shamir. This gives us, in this case, just a security argument based on some hard search. So it asks you to find a commitment such that the commitment commits to polynomials which are 0 at the positions which the output maps to, right? And this is actually gives you an information theoretic argument that you can go over. So why is this cheap? Because we actually don't need to stretch. So you just have this information theoretic argument instead of having to extract it. And that's something we can do, and we did. And so in the end, our proof strategy ended up to be, we reduced the protocol to 3 rounds, then we prove must verify 0 knowledge. This is pretty standard, so I will not talk about it. We prove sounds in the Q round, slide, and then we apply round results. So we have this adaptive reprogramming paper from Asiacrypt 21, where we show how to deal with the signature queries, and then there's this paper which I mentioned before, which gives you that if you have a special sound rerun with an open protocol, you get you have a security, so security against So this means the main thing we had to do was proving special soundness. And as I said, we don't get perfect special soundness, but we get some computational version in this case. So this means we suddenly have to consider the algorithm that produces the 2 transcripts. And we can prove that as long as this algorithm is computationally bounded, so it makes at most a certain number of queries to the random oracle, then we can bound the probability that it outputs two transcripts which fulfill the pattern, like same commitment, different challenges, such that they both accept transfer verification, but the extraction. And give an explicit bound for this. I will go over the bound in seconds. Something that the reviewers complained about is this bound is actually a search problem stated in something called the Qron plus. This bound is actually independent of the Qron plus then. So the Qron plus vanishes again afterwards, but we need this Qron plus formulate the search problem. Let me briefly explain what this model is. So this model works as follows. Adversary is a two-stage adversary. It interacts with the random oracle, and this random oracle has to be implemented by a sandwich compressed oracle. And the adversary makes its queries as usual in the beginning. And then the second phase, before it outputs its solution, it actually gets a measurement of the internal states of the database of this compressed oracle, and can use this to output the solution. Why do we need this? The reason is that we build a reduction, for example, this important problem, and our reduction runs an adversary scheme, and we know that this adversary actually solves the search problem. This is reflected in the queries to the random oracle. The problem is because when we QRun, we don't see these queries. So we are making these queries to the outside, but we don't know what's in there, and therefore we cannot solutions. And this is exactly what this model gives us, because in the database, we later on find a search problem. Now you might say, okay, this is a much stronger model than the QROM, that you have in addition this access to the database. But if you think about it in an information theoretic sense, this is kind of as if R is oblivious, right? So R, like the reduction in some sense, if you take the adversary, like the reduction together with the adversary, and this algorithm has knowledge of these queries. It's just in the wrong part of the algorithm. So this measurement doesn't give you anything new information theoretically. It just gives you the information back of what you did. And therefore, you can actually prove that the search problems, conventional search problems, are not easier than Qron plus. Same bounds actually directly. That's a generic result that was proved. Yeah. So then we get the following bounds. For no message attacks, we get the server decoding advantage. Then the special soundness term, which I will comment at the moment, plus some term from the Chimere transform. If you add the chosen message attacks, then you get the unverified zero knowledge term and an additional reprogramming term. And actually, this is pretty much as tight as it gets. If you look at this, I don't know why I didn't circle this one. So, of course, if you can break syndrome decoding, you can compute a secret key from the public key, so then you're done. The next term is actually the bindingness of the commitment. You can find collisions. You can break this because we're implementing this via random oracle. So this means you're getting a collision bound. So finally, this is compute minus the commitment. Then you have two Grover search bounds, and these are ones for the message compressing random oracle. I can find a pre-image of the challenge, I can break it. And similarly, if I can find a pre-image of the points challenge, which I have to evaluate the polynomial, I can also break the scheme. Then I have a search bound for the highest commitment, the randomness can be break it. I have the standard PLG advantage, and for the reprogramming bound, we have also shown the matching attack actually in the reprogramming paper. The only thing that's actually in there, which is non-tied, are these two terms. And these come from multi-target attacks, and you can easily prevent them by actually domain separating your POG and your commitment. And this is something we did in the implementation, but we didn't consider it because this would have made the proof massively less readable. And it's a pretty standard technique. You can show if you have separated challenges, then you cannot use a single query to attack. So this is actually also implemented, and you see you don't lose anything in terms of speed or anything, but because we go from 3 rounds, from 5 rounds to 3 rounds, where we group the first 2 rounds, or the first 3 rounds, you actually, if you look at this as an online-offline signature scheme, you do pre-computation of everything that you can actually compute before the message is necessary. Then this shifts a lot more computation to offline. So the online phase is really just a tenth of a millisecond. Or 10 seconds. While most of the computation is in the offline part. And in the paper, we also discuss a proof of work technique, which increases the cost of the message compression function. And thereby, for example, here it allowed us to remove one of the parallel repetitions in the verification scheme that you need to boost the soundness, and then this allows you to actually reduce the signal size quite a bit. You could drive this further, so it doesn't really limit to it, but this was one example parameters in. So to conclude, we gave a new security proof the Q-ROM as being the head and hypertext version of it. Advanced time up to these constants, which vanish the use of target attack protection. It gives you this online-offline signature with a very short online phase. So if you have a setting where you can do pre-computation, this is actually extremely efficient. The techniques in general might apply to similar schemes. We're currently working on this, and it looks as if for many similar schemes this will directly apply. And we have this proof of work approach, which is similar to the Sphinx plus C idea, which you might have seen, which allows us to optimize parameters.
You mentioned that there's this reduction that you can get rid of the Q-ROM plus in your assumption, but my guess is that this means that the university needs to simulate the Q-ROM plus, right? And the first protocol is computationally relatively expensive. So is that a type reduction or non-type one at this point?
What we proved is that the bounds are identical.
So the runtime might go up.
No, the runtime of the adversary is the same. So it's not a reduction proof. It's showing that it's really giving explicit bound. But in this case, just the challenger simulator.
Okay, thank you.
Next to make it possible to attend the membership meeting, I think we thank Jeff again. It's by Cryptography. It's a new formulation, so we have a problem and for less significant.
Thanks, Andre. So officially the membership meeting starts now. So I want to thank you for being here instead of there. And for being here at my talk. I'm very happy to get this work. This is actually a joint work with Paolo Santini from University of Technical Market. I'm sorry he can't be here with us. That's why I put his name on the slides. But you will find his name after the show. So, okay, enough of the preliminary since we are already late. here is the structure of the talk. I will give a quick background, although I'm likely to be last in the session, so by now I assume you've seen enough of cryptography. And then I will talk about signatures from equivalence, and then come to the content of this work, which is an reformulation of the problem, and explain how it gives us concrete advantages of the previous associations. And finally, we'll give some conclusions. Okay, so for background, like I said, we are at the end of a code-based session. So this is a general recap slide of basic coding theory facts, which you have seen before. But in fact, I want to point out just the attention to this idea of information set, which is going to be important for the work presented here, because our organization builds around this idea. So information set is simply a set of columns which carries the information symbols in coding theory perspective. So in other words, we consider the submatrix form by its columns, and we check whether this is invertible or not. We can get the identity matrix from it, and this is information set. Okay, so we'll come back to this idea of information set. In the rest, we just work on traditional codes that find the vector space of Q, and interestingly, in code theory, we're interested in correct errors, and this kind of translates to cryptography as well, because in fact, while in code theory we use codes to correct errors, in cryptography traditionally we won't have. I mean, cryptography views have problems, and therefore the ones from coding theory have these problems with the coding, like the ones you saw earlier in the session. And so, in fact, when we consider a random code, so a code which generates randomly or it looks random, right? We don't know the structure. The problem with the coding errors in this code is hard. In fact, it's proved to be incomplete. We have actions like we've seen before in the session. We have Linux solutions, so we have a lot of coding ingredients to make the problem. And in particular, what we like is that we have algorithms that are very well understood for a this problem. And so, traditionally, the way we do cryptography is to use some problems, such as the coding problem, and Hamming method is definitely the most popular one, or at least the most traditional one. And when we do encryption in the cloud, it's usually so we have to mask our private code, which allows us to code into a public one, which instead should be random. So, and so, in fact, like you've seen, for example, in Marco's talk earlier in the previous session, the traditional way of masking this code is to use the standard tools from coding theory. So we change bases, and also at the same time we apply permutation of the columns, which brings us into what is called the equivalent. And we will see more details about this later. But these two operations together are supposed to mask the code, right? And I say supposed because, of course, then the hardness becomes an assumption, which also mainly depends on which code family you're trying to find. In many situations, if you try to find codes, it just doesn't work because they're too recognizable. But for example, somehow miraculously, right, as we've seen, binary copper codes in certain regimes, we're still able to do this, which is what allows these algorithms to still stand. Right? So we're seeing classical release, and this is one of the finalists at least, together with batch and HPC. So I think it's fair to say that code-based encryption is in a relatively happy place right now. But signature schemes have a long history, I would say almost as long as code-based encryption, and they have not been so happy and recently. So essentially, we just have to do things a little bit differently because using the traditional trapdoor approach, it's not ideal. And so here, I want to take a step back and go back to the notion of function, which was popular throughout various sessions. I want to say, and just in case you haven't attended one of the earlier sessions, just recapping here what a function is. The very standard tool in mathematics, right? Is the action of a group on a certain set, which maps G and X into G star X, with the only requirement that this map is compatible with the group. And of course, if that's what we have, maybe we can't do much with it, right? So we have to add some properties. In particular, when we talk about cryptographic group functions, we want to have properties that are of relevance in cryptography. For example, efficient evaluation, sampling, and membership testing are at the very least desirable. And then also for cryptographic purposes, we want to have a hard vectorization problem. And, what is the vectorization problem? It's simply the problem of finding the map connecting to set elements, if this map exists. Of course, I didn't talk about several other properties that a function can have, such as transitivity, freeness, and commutativity, and so on, which characterize the function in several different ways. Right? But from a cryptographic point of view, this is on top of the standard mathematical properties. And if you still are wondering what this object actually is, well, the very famous example here is exactly this problem, right? So we have, in fact, a group acting on another group, and this vectorization problem is exactly that. Okay? This is actually a very special group action with a lot of extra properties. But of course, so we can use group actions. Now you know, wow, we have this logarithm problem, so you can do a lot of things with this, right? And one of the things we can do with it is build zero-knowledge schemes, which immediately yield signatures as well. So for us, what we are going to look at is this standard way to design a three-pass sigma protocol, which more or less looks like this. We have two public set elements connected by a secret map G, and then we commit to a random instance x tilde, which is obtained via a random element from the group, right? And then essentially we have two possible challenges. If the bit is 0, then we reveal the ephemeral map. It's kind of like a consistency check. And if the bit is 1, then we reveal this map on the other side, which contains the bits. Yes, and so we show that we're always able to complete the diagram from both sides. And then this, of course, gives us a protocol that sounds. Okay, once we have this, it's a short step away from this to a signature scheme using, for example, the Sherman transformation. Right? But of course, if we do this, and we do this, right? We do this or similar to this anyway. It's not very problem. We have recorded signature schemes, but these are not postponed. So then we have to, maybe use some other tool. But in general, this framework is perfect. Right? So what about group actions from coding theory? This was the original question when I started this line of work a few years ago. Well, in fact, it turns out that we have such a concept in coding theory as well. Here we have to take a look at what maps we have available. And it turns out they are exactly the maps that I was talking about before. So in fact, these maps are exactly the isometries for the Hamming metric. And the word isometry means a map that preserves distances or the weight, right, of the code. So you preserve the distances between the code. So naturally, you can think, okay, what preserves the Hamming distance? Well, permutations do, because you're just permuting columns, you're just permuting elements, so you're not altering the Hamming weight, which only depends on the element being 0 or non-zero. And then, of course, you can build on this, right? So not only permutations, but you can also employ maybe permutation with some scaling factors. Of course, if your position is 0 and you scale it, it's going to remain 0, and vice versa, if it's non-zero, it's going to remain non-zero. So as long as you employ non-zero scaling factors, then you have this kind of augmented permutations with some scaling factors, which we call monomials. And then you can even throw a little morphism in there, right? If such a morphism is available. And so you can see, you can say that two codes are equivalent if they are connected by an isometry and they are not equivalent. So it's a really important notion in theory, in fact, whether two codes are equivalent or not, because it means that essentially geometrically the two codes are the same. Just depends on which order the coordinates are represented. Well, you can see a very quick example here in which we just permuted the elements, but the distance between each code word is preserved. Okay, so the notion of equivalence just means that all the weights in the codes are and therefore the distances are less. And because we have three flavors of equivalence, we talk about permutation equivalence, linear equivalence, and semilinear equivalence. Okay, well, how do we describe this map? Well, this is particularly easy because each code can be represented via generator matrices or matrices like we saw in our summary slide at the beginning. And clearly, for example, if you use generator matrices, two codes are permutational equivalent if there exists change of basis and a permutation such as G prime. Okay, and similarly, a code is linear. Two codes are linearly equivalent if there exists a change of basis and a monomial matrix Q, which is just a permutation with some non-zero scaling factors. Okay. In effect, so we're getting to the point. It is can be seen as a compaction of this group here on the set of current matrices, which are exactly the generator matrices. The compaction is just simply given by this operation. And in fact, if we choose a canonical representative, so we know that we have many choices for generator matrices, but we can focus on, for example, the systematic form where we have the leftmost block as the information set, and then we choose that to be the identity. Then that is a canonical representative for the code. And I've highlighted this word because in fact the word is exactly about different representatives of these codes. Then in fact the group G is acting on the entire code. It doesn't matter which generator matrix I choose for. And it's important to note that here X is not a group anymore. So unlike the rocket example, but also unlike the case of isogenies, for example, the action is non-commutative. And so this prevents both short algorithm, which is of course the foundation of the work, but also other algorithms like the algorithm. So by this I mean that in fact the non-commutativity is for some purposes an obstacle, but also a feature. And so once we have defined the compaction, we can look at the hardness connected to it. And in fact, the problem of deciding whether two codes are equivalent is well known in coding theory, right? And it's the well-known hard problem. And for cryptography, we traditionally call the computational version of this problem, which is exactly the vectorization problem. Right? So given two codes, find a map that connects them, or equivalently, you can say, for example, if you take systematic generators of the codes, find the monomial matrix Q such that G prime is systematic for okay? So this is what we call the linear equivalence problem, and is a formulation that we're interested in. The permutation case is simply a subcase in which we choose the monomial to have scaling factors of equal to 1, and we have permutation. And in fact, in practical application, we kind of ignore the semilinear version because it just does not add much to the security, right? And also use prime fields. So in general, we do not worry about the semilinear version. We just work with the okay, so we have a code-based compaction, hard problem connected to it. How do we use it? Well, we apply the same framework that we saw before. We obtain a zero-knowledge protocol, which is based exclusively on this hardness, right, of the vectorization problem. We did this in 2020, and the protocol goes more or less exactly like the picture, right? So we choose a random code C, then we choose a random monomial matrix, the Asiacrypt, and then we publish G prime, which is a systematic form of G tensor. So now we have G and G prime as our public elements, and the prover interacts with the verifier by committing to a random instance. So I choose here like tilde, then tilde, then I hash it, then my commitment, and then I receive a binary challenge, and I answer either with the ephemeral instance or with the instance that actually contains my vectors. And you can see here that you can verify either from G or exactly like we saw in the diagram. Okay, so this is extremely simple translation of the framework for generating functions to the base. Okay, and in fact, because the protocol is standard, it's immediate to prove the completeness of the protocol, the two special soundness, the knowledge protocol. So we have a strong condition to build on. And then, like I said, it's only one step away from applying Fiat-Shamir, the step being able to iterate times, in particular here, because the soundness is 1/2, we iterate lambda times, where lambda is our security parameter, and we're done. Of course, this is already better than previous attempts like Stir's protocol, where the soundness was 2/3, but we want to do even better. And in fact, we have some optimizations that are possible because of the function structure. And we did this in 2021, where we used multiple public keys and non-binary challenges. So now instead of using a 0 or a 1, we have multiple public keys, and my challenge is non-binary, instead select one of the multiple public keys to verify from. This lowers the soundness error, but occurs in a rapid public key size. But also we can exploit technical tricks. For example, we use a challenge string with fixed weight omega, where we minimize the number of instances of the one type, and we maximize the number of instances of the zero type, because these instances are purely random and can be represented via a C, or a random generator. This is a well-known technique. So we exploit this imbalance, but we increase the number of iterations. So there's always a trade-off, and combination of these two decisions together takes us to various choices for parameters. Okay, it's important to point out that applying this is very standard and in many schemes, and in fact does not require modification at all to either the security aspect. So we only tweak the application of the forking lemma or base ourselves on an equivalent problem. And from a design point of view, of course, we have to pay attention to the hardness of the problem. This is characterized by several solvers, but importantly enough, once you avoid weak instances, the best generic solvers for the linear equivalence problem sort of connect back to the idea of decoding, because in fact, decoding and looking for code words of a certain low weight is kind of the same thing. So what we do is very short. Look for code words of the same weight in both codes, and then try to deduct the map from these two lists of code words. So in the end, we have a variety of solvers that have been refined over the years, and they're all combinatorial in nature. These are the most efficient solvers, and so we can actually categorize these via ISD, which is the same algorithm. And then we choose parameters to make ISD hard. So we just set our requirements in this way, in a very conservative way. We just want to make ISD infeasible from the beginning. For example, for category 1, which is about 128 security bits, we have this choice for code length, dimension, and cube is the size of the field, so 127. Okay. Okay, so then of course, after you fix the code, the protocol parameters are the ones that equate the performance profile, as I mentioned before. You can choose multiple public keys, you can choose different number of iterations depending on our priorities. And you can see that the public key is dominated by the size of a single generator matrix, just S minus 1. First, if you want the first matrix is random, right? The many S minus 1s are not random anymore. So it's K minus K in systematic form. And then the signature is dominated by the cost of transmitting an isometry. So we have omega iterations that transmit a full isometry, which is a monomial matrix, plus some seeds and salt and some other part, which does not depend on. Okay? So with this in mind, we also have to mention that the runtime is dominated by system of computation, because we use matrices always in systematic form. And we have a lot of flexibility in the protocol, but essentially the length of the signature kind of behaves like n log n, very roughly speaking, and we would like to reduce the signature size, press it, and this is a first step towards doing that. Okay? So we get to the core of the work, which is how to reformulate the problem to compress signatures. And let's start from the presentation case, which is the simplest one to analyze. And then we will see that, in fact, when we step to the linear case, everything kind of works in it. So when we transmit a permutation, in fact, applying to the generator matrix, we have three types of information that we are communicating. Right? First of all, we are communicating which of the columns are moved to the k leftmost coordinates. Because for now, we're just imagining that we are looking for the information set in the first leftmost k coordinates. Okay, so which are the coordinates that become the information set? And once you determine which ones are those, then there's like n minus k columns left. And so you have to determine how these k columns are sorted and how the remaining n minus k columns. Okay, so a single permutation kind of tells us which columns should I move to the left, and then how do I move them, and how do I move the remaining. Okay, and in fact, once you look at it, you can represent these three formations via three different permutation matrices. right? So we have an n by n permutation matrix PIS, information set, a k by k permutation matrix in P rows because it's well, kind of like a row operation, and then n minus k times n minus k permutation matrix P columns. Okay, so in fact, any permutation we can decompose it into PIS times this block matrix here. And now here I'm using the inverse of P rows rather than P rows itself. We'll see later, it just makes calculations later, but of course this is just one matrix, so its inverse is kind of the same for the diffusion purposes. Okay, so the core idea is that we have three categories of information that are carried by the permutation matrix, and we decompose our permutation according to this type of information. Okay, so suppose that J is the set of coordinates that becomes the information set, right? So it's a set of coordinates that is moved to the leftmost K. And then when we apply this PIS to the generator matrix, it means that G restricted to the set J is moved to the left, and the remaining columns are moved to the right. Correct? So this is exactly what the job of the P information set matrix is. Okay, so this sort tells us which columns to move to the left and which ones to move to the right. Once we apply the full permutation, then Yes.